Well, hey there, HVAC pros and enthusiasts. Are you ready to take your skills to the next level? The HVACR Learning Network has just launched an exciting new e-learning course, High Performance Heat Pumps. And guess what? We're giving you free access to the first 2 chapters. Whether you're in the field, training for that next step, or simply want to sharpen your expertise, this course is packed with everything you need to understand and master high-performance heat pump systems, especially inverter-driven cold climate heat pumps. And the best part? You can access it anytime, anywhere, right from your favorite mobile device. It's HVACR learning made flexible and convenient for you. So what are you waiting for? Click the link. Dive into the HVACR Learning Network and start your free trial today. Your journey to HVACR mastery begins here.
At Service Logic, we believe the future of the skilled trades lies in training and development. And that's why we created the Edge, a platform dedicated to empowering our greatest assets, our people. From hands-on training to leadership development, Edge is where technicians grow their skills, expand their opportunities, and build lasting careers. Because when people succeed, our companies, our customers, and our industry thrive. This is the Edge. This is the future of the skilled trades.
I chose iConnect training equipment because I already previously had some iConnect training equipment, and I was very pleased with the equipment I had, the quality of it, and pre-designed labs that came with it. So when I expanded it more into the catalog, I decided I wanted to get this refrigeration trainer in my program to expand my program. My experience so far using the TU-155 has been pretty good experience, especially my second year students, and the light bulb kind of syndrome goes off when you see that little flicker in their eye and they're, oh, I got it. That's what us instructors, what we look for is the I got it moment. And this helps me to the I got it moment with my students, and that's what's my goal to achieve.
We are Daikin, the #1 global indoor comfort provider. Our innovative home and building solutions are engineered with energy efficiency and sustainability at their core, ensuring improved indoor air quality for all. From heating and cooling to ventilation, air purification, refrigeration technologies, and connected devices, we're at the forefront of technology, addressing the pressing challenges of sustainability.
Well, hello everyone. Thank you so much for joining us once again on Did You Know, the ESCO HVAC show. We are actually hanging out at our office in Mount Prospect, Illinois. So for any of you that have ever called the customer service number before, the office number, it's actually where we're hanging out today. So we're here to have our annual meeting and get together, and we're going to have a Christmas party tomorrow night. So we're all a little Christmassy. Eugene's a little naughty over here.
No, sorry.
But we're having a lot of fun. We're so grateful that you're joining us, and let us know where you're joining from. It's so cool to be able to see how large our community is growing. You know, a few weeks ago, Jocelyn and I did a episode where we were talking about thermoelectricity, using this thermoelectric fan here, and talking about that principle because it's a function of heating and cooling and even ventilation, right? Well, what are we doing there? Well, remember we talked a lot about the whole process of converting heat into electricity and then utilizing that electricity to be able to run the motor. So let's looking for a zoom in. Oh, there we go. Yeah, I can start putting those up. Hey, Kendrick. Hey, Kendrick's right here in the area.
What's up, Kendrick?
Appreciate you joining us today. That's right, Chicago.
Southside.
Hey, Coldfaker, San Francisco. Cool. That is great. David Harrell at Cincinnati. Hey, Garrett. Glad that you're with us again today. Hey, you got your students in the classroom, or are you just hanging out there? Yeah. Oh, you're on the nice list in Bloomington? Well, we'll see if we can't get Eugene on the nice list before the end of the show. We're hoping so. It's hard to keep him in line sometimes, but we're going to give it a try. So in our conversation, one of the things that I asked everyone is, would you like for us to go a little bit deeper into semiconductors? Because we were utilizing semiconductors for this process. And it's really not my specialty. I took some electronic classes in high school, understood the principles, but I couldn't go deep into that. So we brought in the professor to help bring.
No, you told me you were trying to find an expert on electronics, and that because you couldn't find one.
Oh, is that it?
You settled for me. That's at least that's what he told me.
Yeah. Well, you all can believe what you want. I know for a fact we all know Professor Silberstein as this amazing instructor of HVAC and refrigeration. But did you know that his specialty is actually in electrical engineering, electronics?
Scary but true.
It is scary but true. So we're going to dive a little bit deeper into the. Oh, I think that's our meter. Yeah, that's okay. We'll come back to that. We're going to dive a little bit into our electronics and understand how these semiconductors are doing that work for us. So yeah, you're right. He sure is. So we're going to go ahead and dive into our presentation. We're going to do a little recap on some of the things that we talked about last week. So if we think about that thermoelectricity, right? We're utilizing heat energy to be able to move electrons, excite electrons really, so that they get moving, and we are now going to be able to generate electricity from that. So let's move forward a little bit. And probably have to go over to that one. And it'll be the bottom left there.
Too many buttons.
Yeah, we got a lot going on here. We got a mobile studio set up right here in the office.
If you saw what we're looking at right now.
Yeah, there's a lot. I'm going to turn this silly thing off. It's saying, hey, you forgot to turn me off earlier. We'll turn it back on here in a little while. One of the things that I got hung up on, hey, how's it going? Appreciate you joining us. I'm not going to try to pronounce that. I'm going to say Mr. Bashir. I'll be safe. How about that? And let us know where you're joining from. Love to know. You know, one of the things that I got to, and we had some questions on, and I couldn't go deeper, was that design between the N-type semiconductors and P-type semiconductors. And Eugene is here to help us dive deeper into that so that we can see how they work together to be able to create the flow. So what do you think? You want to begin here, Eugene?
Yeah, so we can actually hop in. So when we often hear the term semiconductor, and we typically associate semiconductors with silicon.
Yeah.
So people by default think, okay, well, so silicon is a semiconductor. Well, actually, silicon by itself, pure silicon, does not conduct electricity.
Right. Be an insulator?
So yeah, it actually really is.
Okay.
So because what happens is the atomic structure of silicon, it actually has 4 valence electrons. So if you look at your screen, silicon creates this really crystalline structure where it shares its 4 valence electrons with each of 4 silicon atoms that surround it. And as such, they create these completely full outermost shells.
Okay.
So a goal of an atom, without getting too crazy, is to become neutral. So it really wants to have a full or empty outermost shell.
Not in between.
Yeah, so it wants to be completely full.
Okay.
If it's completely full or completely empty, basically the same thing.
Right, it's stable.
And then it's not going to give up electrons.
Sure.
So that's where it wants to be.
Okay.
So when we talk about electricity and electron flow. We're talking about the flow of electrons.
Mm-hmm.
But if a substance doesn't want to give up electrons,
Right.
they're not going to flow.
Yeah, I don't want to move.
Yeah. So what we do is we actually dope or add impurities to silicone. And when we add impurities to silicone, we add elements to the silicone
Right.
that have either more or less than 4 valence electrons. So for example, boron and phosphorus are common elements that we use to dope silicone.
Okay.
So when we add boron or phosphorus to silicone, we either create a crystal that has extra electrons,
excess.
or we create a material that has a deficiency of electrons.
Really?
So when we have an excess of electrons, then that means we have more negative material. So we actually create what we call N material, and N stands for negative, which means we have more negative charges.
Sounds pretty simple.
And then if we use an element that has fewer than 4 valence electrons, then we end up with a hole. So now we have a deficiency in the crystal.
Yeah.
And now we end up with a deficiency of electrons, which means that the substance is more positive.
Really?
So if we add more electrons,
Yeah.
then we end up with what's called an N material.
Yeah.
That's negatively charged. And if we add a material that has fewer electrons, we create P material. So it's still, for the most part, it's still silicone, but it's doped. We're adding impurities to the silicone to create a material with a net positive charge or a net negative charge. And now, when we take these materials and we put them in intimate contact with each other in different configurations, we create the basis for electronic circuitry. So, basic electronic circuitry, it's like electricity, but just a lot smaller, right? When we're talking about electricity, we're talking about the flow of electrons.
Absolutely.
And when we put a positively charged substance, in contact with a negatively charged substance, we're going to have the movement of electrons. So what's neat about electronics is we're moving electrons and we're starting and stopping electron flow, but we're doing it a lot faster. When we talk about electricity, you have a light switch on the wall,
right?
And you need to physically flip a switch to start and stop the flow of electrons,
right?
But when you think about computers, how are we able to do millions and millions of calculations a second? We do it electronically
with very, very small.
So we don't have to physically move contacts.
No
we do it based on the properties of these N materials and P materials. So it's actually kind of neat. We can,
that actually brings up something, and maybe I'm wrong here, but thinking about that in a slightly larger perspective with like battery storage, right? Like say if I've got 2 AA rechargeable batteries, which is what I use in most of our microphones. Yeah. If I have those 2 and I've got a negative on one end and a positive on the other, and my other battery's got a negative and a positive, and if, like say I had 1.6 volts in one battery and 1.4 volts in the other battery, when I put those negative and positive together, they like to try to balance each other out. Is it a similar philosophy?
It is, but what happens is with battery storage, if we create a charge on a battery, and we don't connect that battery to any external source, that charge has nowhere to go.
Exactly.
So that charge is going to be stored in the battery. And then if we connect the positive terminal to the negative terminal, the electrons are going to flow
and go try to balance
from the
out.
Negative side to the, and that's actually kind of confusing because we always say high voltage goes to low voltage, like the positive side on the battery,
low,
but with electron flow, it's actually the other way around because electrons are what's moving. So although we say high voltage goes to low voltage, if you look at a battery and you see the plus terminal and the minus terminal, the electrons are actually moving from the negative side,
trying to get to
the positive side, which is actually that's
pretty crazy,
kind of cool.
See?
Stuff.
I'm telling you, we learned some crazy things here, Jocelyn.
But it's actually really funny because when I've you mentioned I have a strong electrical background,
Right.
and even when I was as young as 6, 7 years old, I was working on electrical circuits,
Wow.
and I understood electricity because I could see wires and I could see
Right.
switches
It's
and I could
physical.
see relays.
Yeah.
And then when I went to college and I was doing my electrical engineering degree,
Yeah.
I aced all of my electricity classes.
Right.
And then when I took my first electronics class, I failed it miserably. If there was a grade lower than an F,
Right.
I would have gotten it. I had absolutely no clue. And I'm going to show you actually, because
Okay.
my dad was in the trades.
Right.
And he actually drew me a really interesting diagram that clarified everything.
Yeah.
Because I knew electricity, but I couldn't bridge the gap.
The physical component of electronics.
Yeah. So
you're going to enjoy this. This is really cool. It's going to be a little bit, but we're going to get there. I
Yeah,
promise.
we'll get there. But
We're walking all the way up to that process. And if you have any questions along the way, let us know. Throw it in the chat. We're here for you. That's the whole point of this conversation. So this is where I thought it got interesting. I mean, I was kind of understanding the principle, but now that you're talking about this, I'm starting to see it a little bit different. Yeah, a little shell shock. Yeah, Garrett, that's what it was for me. My immediate response is, okay, I need to learn more. Let's go to Professor Silverstein and let's talk about this, because here on our show, we pride ourselves in taking fairly advanced concepts and making them understandable, because as educators, it's our responsibility to understand things so comfortably that we can communicate that to our students. And as technicians, it's the same thing, right? We need to be able to understand. And when we can see it more, at least for me, if I can see it, I've got a better understanding.
Well, you know what? I mean, thermoelectricity is kind of neat, and we could talk about that, but let me ask everybody a question. So visualize yourself holding a piece of copper pipe. All right, there you go.
Got it.
Oh yeah, there you go. And if you hold one end of that copper pipe with your hand,
Yep.
and you take the other end of don't do this at home, by the way, and you take the other end of the copper pipe and you put it and you hold it in an open flame.
You're right.
Well,
Turn it around, put it into hot.
no, you hold it with one end. Don't hold it with that
Okay.
end. You're going to burn that hand.
Okay.
Right. So if you hold a copper pipe, one end of a copper pipe, and you hold the other end in an open flame, how long are you going to be able to hold that pipe before that copper pipe gets really, really hot? But what's happening to that? Right. You're heating up that copper pipe.
Right.
The electrons are vibrating. They're moving. They're transferring their heat energy.
Right.
So we have copper pipe, which is a good conductor of heat. It's also a good conductor of electricity. We're talking about the movement of electrons.
Yeah, exactly.
So when we talk about thermoelectricity, it's really about moving electrons from a warmer substance to a cooler substance. We kind of understand that.
Sure.
We're in air conditioning. What do? We take heat.
Yeah, we move heat.
And we move it. We're BTU movers.
That's all we do.
Right? We move BTUs out of a house when we want to cool it. We move BTUs into the house when we want to heat it.
Yeah.
But the whole concept of thermoelectricity, thermo, heat, electricity, right? The movement of electrons. So this is actually really, really neat. So we have all of these little pairs of P material and N material that we just spoke about. And we have all of those connections in series with each other, and they're all generating little bits of electricity, bits of heat, right? And as such, we're actually generating the flow of current. And the way thermoelectricity works, basically, is we have a hot surface and a cold surface, and we already know that heat wants to move from a warmer substance to a cooler substance, and that's also the movement of electrons. So it's really just an extension of something that we're already teaching. We're already teaching. We're already understanding. We're already implementing in our daily jobs. Right. We're moving heat.
Why wouldn't we want to add this into our own discussion and curriculum? Because it helps the world around us make more sense when we can start understanding how these things work, taking some of the magic out of the.
There you go. But we can even break that down even further. I mean, that's like a complete module,
right?
That's something like this,
right?
It's like where you have all of these little, PN junctions, these little NPs, and we're going to talk about a PN junction because maybe you might not have heard of a PN junction, but maybe you've heard of a diode. That is a PN junction. But this discussion goes into diodes and transistors and solar panels and pretty much all of these fun things. And it all boils down to that previous slide where we're doping silicone to create positively charged material and negatively charged materials. But yeah, it all has to start somewhere.
Yeah, exactly. And it's so intertwined. Love it. Okay, so let's think about then. Let's move forward a little bit to see like what's happening as we pair these N and P materials.
So this is that previous slide, but this is a portion of it. So that bottom gray plate is the hot surface, and the top surface is a cold surface, and then we have pieces of N material and P material. So here there's just two of each. It could be one of each. It doesn't matter.
It shows how we're flowing to build from one to the other.
Yeah, the way it happens is if we dope silicone with a material that has less than 4 valence electrons, we end up with what we call a hole.
Because
it's where an electron should be, but there's nothing there.
It's a hole. Realm's not full.
Yeah. So we create within the crystal itself, we end up with a hole that an electron could fall into. So we end up with an electron, excess electrons if we have P material, and then we have that hole. Actually, we have the hole in the P material and excess electrons. I misspoke. Sorry about that. So here's what happens. So when we heat that hot surface, that's okay.
That's all right.
And what happens is electrons move through N material from the warm surface to the cool surface because the N material has an excess of electrons. So now those electrons are moving just like they moved when you held the copper rod in the fire.
Exactly.
All right. So the electrons move. So now picture electrons moving upwards
up on the end
through those yellow pieces.
Yep.
But now in the P material, think of P material as the opposite,
it's the opposite
of the N material.
Flow the other direction.
So the holes on P material move up in P material, which means the electrons move
through it
down. So now follow the path. So on the left side of this diagram, you have a red wire that's marked plus, but now that red wire goes into the N material, but because that bottom plate is warm, the top plate is cold, the electrons go up through the yellow, and then they go down through the blue. But now look, the outlet of that blue is connected to the next yellow, which is the N material, and the electrons go up, and then they go down through that last P. Now, if you have 10,000 of those, you constantly have electrons moving, so it's like a lot of batteries. You ever buy a little toy and you have to put multiple A batteries in it?
Yeah.
Well, so the outlet of one battery is connected to the inlet of the next outlet, and that's this. So we have all of these little micro batteries that are all connected in series with each other, and the more of those little micro batteries we have, the more voltage we're generating.
Exactly.
So when you see a thermoelectric generator, like we had on that first slide, that whole plate, there's tens of thousands of these little micro batteries that are all joined outlet to inlet, outlet to inlet.
And imagine manufacturing is what's changing the availability of them. Because I can remember, a decade or two ago, here was $100. Now it is like $5. So let's grab the OBSBot one. I should have brought that one back up, the big red one down at the bottom there. And let's go to preset 2, and then let's trade
whatever Jocelyn's doing right now is way above my pay grade.
So what we're talking about is right here. Okay, so this is our plate, and it looks solid until you dive closer and realize, well, this is exactly what Eugene was just instructing us through. So sitting here idle, we're going to go ahead and fire these up and kind of take a look at them while we're having this conversation. So, and this would be a DC voltage, correct? So we'll put this on a DC voltage. We'll go ahead and get a backlight on that for you so you can see we're just kind of stable. We're going to go ahead and apply heat to this. And let's see if we start getting some changes in our voltage. And so we're just going to monitor it for a little bit, see what it's doing. There we go. So we're going to start applying voltage. We're going to just watch for a while and see what's happening here. And already some changes starting to happen. Okay, so let's
Oh, I should get some bread. We can make some toast.
we probably could. This thing will get pretty warm. As long as my leads and all are working fine here, which I should have pre-checked those before we got there. So while that's warming up, let's go ahead and go back to our presentation, and let's go ahead and go forward a little bit. Anybody have any questions while we're right here? We got quite a bit more to get through in this next half hour or so. All right.
That's everything we just spoke about.
That's all right. There you go. This is what it's actually doing. And I love this because this is a thermocouple, right?
Yeah.
That is the entire principle of a thermocouple.
Yeah. So yeah, if you're looking at milliamp systems,
Yeah.
right? What is a thermocouple? A thermocouple is a hot junction and a cold junction.
Yeah.
So same concept. You have two different metals
Yeah.
connected at a hot junction, and that's the junction that you're using to sense temperature.
Sure.
And that's creating this millivolt
Very
signal.
low voltage.
Yeah. So
Okay.
it's the same concept. So we've been using this stuff for quite some time.
Okay. All right. Well, so if we start moving forward. All right, there's our fan. Let's go with another one. Okay, so here's kind of what you're talking about happening. Oh, hey, looky there. We've already got some movement. Right? So
Oh, my biggest fan.
look at that. I must have had some lead problems here because it's still not reading properly. But at least we're already seeing that we're generating enough voltage. Yeah, those leads are not connecting very well. That was on me. I should have been making sure all my connections were good beforehand.
I might have messed with them before.
Yeah, it was just we're always experimenting. But anyhow, that's what we're seeing is that we're generating voltage from that movement of heat. So this is kind of an explanation of those electrons on those outer radiuses.
Yeah.
right?
So yeah, what's neat is, just to take a brief step back into atomic structure, right? Atoms are made up of three primary elements. We have protons, neutrons, and electrons.
Right.
And the protons and the neutrons are contained in the nucleus.
Okay.
And it's the electrons that
It's coming
orbit
back now, isn't it?
Sure, right? So it's the electrons that are orbiting around that nucleus. And every one of those layers, every one of those orbits around that nucleus has the ability to hold a different number of electrons.
Okay.
So, for example, what you're looking at right now, this atom has 3 electrons, but that first shell, the one that's closest to the nucleus, can only hold 2 electrons. That's the maximum number of electrons it can hold.
Exactly.
The second layer, the second orbit, can hold the maximum of 8. So right now you can see that there's only 1 electron in that outer shell. So yeah, we'll get to that in a second. But yeah, so what happens is that electron is loosely held by the atom. The atom is trying to become stable.
Right.
So either that atom can gain 7 electrons or it can give up 1.
Oh.
So it's holding on to that outermost electron very loosely. If that's like your young kid and you don't really want, you don't care about your kid too much. Like, leave the door open, go out and play in the street. But we would never do that. But that atom would be very happy if that electron would up and leave.
Okay.
So it's holding on to it very loosely. So it's not going to take a lot of force to move. So take, for example, copper.
Right.
All right. So copper we use for wiring. Copper has 29 electrons in its atomic structure, but only 1 valence electron
At the end, on the outer.
Yeah, the outer shell only has one electron.
Okay.
So that electron is very loosely held. So it's not going to take a lot of force to free it to allow it to move on. So as we mentioned, the electrons negatively charged. When we talk about current flow, we talk about the flow of electrons. Right. The protons and neutrons, like I said, they're in the nucleus. Yeah. So when we think about the flow of electrons, people think that copper actually moves through the wire, but it doesn't. It's the electrons. Right. So it's a bunch of atoms of copper, and they're passing electrons from atom to atom. So think about a bucket brigade. So there's a fire at a house, and there's a and there's a and there's a lake with water, and we're trying to put that fire out.
Right.
You don't see people running back and forth from the lake to the house
Right.
with buckets of water. All right. What they do is everybody lines up, kind of like what we're lined up, and what they do is they pass buckets of water from person to person, right? And the last person gets to throw the water on the fire. So this is keep going. This is cool. This is
It is
cool.
fun.
This is fun. So what it is picture Jocelyn, Clifton, and myself all being
Like solid and
all-
stationary.
all being atoms of copper.
Yeah.
But we're passing. I'm running out of space over here.
Right.
But we're passing electrons from atom to atom to atom.
So we're just
So-
slinging them to each other.
But you know what's so funny? People say, "Oh, electrons move so fast." You can actually outwalk an electron because it's moving from atom to atom very slowly. But here, Jocelyn, hold that one. Okay, hold this one. All right. But now watch. No. You're only allowed to hold one. There you go.
Yep.
So now
Okay, make mine back.
Jocelyn is going to pass that ball to Clifton, but Clifton's going to pass. Well, yeah, okay, be that way. But what happens is the effect of Jocelyn passing that electron and the last person in the chain getting it feels like it's moving so fast, but they're actually moving very slowly.
Okay.
You know what? Picture a tube of golf balls
Yeah.
that's full. The tube is full of golf balls.
Okay.
Push one golf ball in from the end. Boom. A
Out the
ball's
other
going to
side,
throw
immediately.
immediately.
Right.
So it's wow, that's really fast.
Right. So it didn't.
But
But not
it's-
like it made its whole lane
No, it's just moving.
little at a time.
Yeah. Actually, electrons actually move really, really slowly.
Okay.
But if you get shocked, it's going to feel a lot faster.
Yeah. That's not a good thing.
Yeah. So that's actually a molecule of, an atom of copper.
Okay.
And you see that one little electron in the
Yeah.
outermost shell. That's actually really cool. But yeah.
And so when we look at different, particularly like in our industry, we always think about different types of wire, how copper wire, aluminum wire, we talk about silver being a conductor, and based on how easily it can allow those electrons to flow can determine how much current we can pass through that.
Yeah.
And if we go even a little bit further than that, and then we look at, well, if I've got a conductor, I've also got insulators. Okay.
Yeah.
So let's talk about an insulator. What does an insulator do?
An insulator just is the opposite of a conductor, right?
Okay.
Conductors allow for the free flow of electrons through a
Right.
substance.
Right.
Insulators, like rubber, plastic, glass,
Resistant.
paper, they don't. They hold on to their electrons very tightly. Like I said, silicone
Mm-hmm.
is a really good insulator
Sure.
until we dope
Until
it,
it's
and then
been
it becomes a
changed.
semiconductor.
Yeah.
Yeah. So when we talk, so that's why we wrap copper conductors or aluminum conductors with plastic or rubber,
To insulate them.
so they don't,
Allow the
facilitate
electron
the.
movement.
Yeah, absolutely.
And it's an interesting thing to think about too. We've learned so much in these last few years about the flammability of refrigerants. That's a big term, flammable, right? And when we first started hearing that, there was a lot of pushback from the industry going, "Oh, I don't want anything that's flammable. That's like gasoline or propane." Well, it's not that it's a clear definition between an insulator and a conductor. It's a broad spectrum, just like that broad spectrum of flammability. I mean, everything's flammable. A diamond is flammable under
Apply enough heat to it,
pressure.
yeah.
Exactly. And so with our insulators and conductors, it's kind of the same thing then, isn't it? Hey, Jose, thanks for joining us. I guess I'm grateful to have you here with us too. Okay, so now it starts getting interesting here.
Started?
Yeah. Oh, yeah.
I already thought this was interesting. I don't know.
All right. So what's in the middle?
So that is our semiconductor material. But when we talk about semiconductor material, we're talking about material that's been doped. Like I said, pure silicone. So we always hear about silicone diodes and silicone semiconductors. But germanium is also a very popular material for semiconductors. But silicone, we dope with boron and phosphorus, and we dope germanium with probably a very unlikely substance. We use arsenic and
okay.
we use gallium
Okay.
to dope germanium. And we can also make diodes and transistors and semiconductor materials using that. So when we talk about the doping process is not, if we add a little bit of arsenic, we're going to dope a little. We're going to,
When
so
you say dope, that's like mixing. Like,
yeah,
like,
doping.
okay.
Yeah, doping is kind of like adding impurities
Okay, yeah.
to the substance. So how much salt do you need to add to water to make salt water?
Oh.
Right? If I have a gallon of water and I add a teaspoon of salt, did I make salt water?
You did.
Yeah. If I have a gallon of water and I add a cup of salt, did I make salt water?
Still salt water.
Yeah. So the term semiconductor is kind of a gray area because it's not a specific quantity of doping material that I need to add to create that N material or P material.
It's in between in some form or another.
Yeah. So it's actually pretty
Thank
cool.
you, Jose. It is. This is really fun information. The industry that we all are a part of is very, very scientific when we start diving deeper into it. But when we can start putting things together, just like earlier, you went, oh, I remember that. I'm the same way. It's like I remember all these bits and pieces, but I haven't been able to apply them in my world as a technician. But now that I'm starting to do more education, it's very important for me to understand how these things work so that I can relay that back to students.
Yeah, but now
educators.
Think about the controls we're using. They're all solid state devices.
Everything.
Relays and contactors.
Yeah.
Easy to see. You can see contacts moving back and forth.
Right.
You can see switches opening and closing.
Yeah.
But the real challenge is at the electronics level, we can't see switches. We see electronic boards and we have wires connected to the boards, and we energize the boards and we cross our fingers and hope we get the right outputs. So what we look at on those boards, we're dealing with these electronic devices, these building blocks, these diodes and transistors and fun things like that. Yeah, but
so they're building blocks for all of these controls that we're talking about.
And we're going to look at them right now. So just
Sure.
to get an idea of how these things work.
Okay.
It's actually pretty neat.
Yeah, let's go ahead and let's move into the explanation that you were talking about. Let's go one more because we see this symbol often.
Yeah.
And so what are we doing with it?
Yeah. So this is a symbol for a diode. And the diode is the simplest building block of electronic circuitries.
Okay.
So the diode is shaped, it's looked like an arrow.
Yeah.
And it has one layer of P material and one layer of N material. So there's one layer of material that has an excess of electrons, the N material, and there's one layer that has a deficiency of electrons, and that's our P material. So the diode has two terminals called an anode and a cathode.
Right.
And the anode is the positive side. So if you're looking at that, the right portion of the diode, that's the anode.
Okay.
And the left side where the straight vertical line is, that's the cathode. So the positive side, the anode is plus positive, and the cathode is negative.
Okay.
Right. So when I'm teaching about diodes, I just like to say it's like a check valve. So if we're thinking about a plumbing application, a check valve only allows fluid to flow in one direction.
Right.
So if we try and push water through a flow check valve and it's going in the right direction, water will flow. If we try and push water through the other way, it doesn't go.
Right.
So if you take a look at the left side of this, all right, we have a battery.
Yep.
And you see the minus and the plus side of the battery. And if we align the anode of the diode to the negative side of the battery, that diode will act like an open switch. It will not allow current to flow. All right. So what happens is the negative side of that diode, all right, which is the cathode, has an excess of electrons. Those electrons are attracted to the positive side of the battery.
Right.
Okay, so that sounds good.
Right.
But if you look at the anode of the diode, that's positive.
You won't allow it to flow that direction.
Yeah, the electrons that are moving
Yeah.
from that negative side of the battery are going to go into the holes in the P
diode.
material.
Right.
So we create what's called the depletion region, which is that barrier, that interface between the P and the N material
Okay.
that electrons cannot pass through.
Okay.
And because electrons can't pass through the diode when it's configured like it is on the left, we say that that diode is open, or it's what we call reverse biased. It's not allowing electrons to flow through it.
Sure.
But now,
Flip it.
let's flip that diode around.
Yeah.
Now, you physically don't do that. There'll be switching circuits that do that.
Right.
But now look what happens. The electrons, now we're looking at the right side of the diagram. So now electrons flow from the negative side of the battery up to the cathode on the diode,
Right.
and like charges repel each other. Right,
Okay.
opposite charges attract, like charges repel, and now the negative side of that battery repels the negatively charged electrons and pushes them
Through the diode.
to the
Other side.
to the other side of the diode.
Yeah.
And now the electrons are attracted to the positive side of the battery. And now the electrons flow through the diode.
Wow.
And you can see that our light is now on.
Yeah, exactly.
So the diode acts like a check valve,
Yep.
allowing electrons to flow in one direction, but not the other.
Sure.
And that's the most simple electronic device that we have. But most electronic devices, regardless of how complicated, are made up of combinations of hundreds or thousands of these diodes.
Very, very small.
Yeah, you can't
electrical
see
controls.
them. You can't see them.
Wow. Okay, so I'm very intrigued with that plumbing analogy. So let's think about this, because the demonstration you use for this is really, really intriguing. If we look at that flow.
Yeah. So you know what? So we hear about diodes.
Yeah.
And we also hear about transistors.
Yes.
And what a transistor is, it's two diodes connected with either their two anodes connected together or the two cathodes connected together. So you might have heard the term NPN transistor or PNP.
Yeah.
PNP, positive, negative, positive, NPN, negative, positive, negative.
So the one in the letter in the middle actually, there's two
is
of
the
them.
common. Yeah.
Yeah.
So it's two diodes connected,
Okay.
with the two anodes connected together or
Right.
the two cathodes connected together. But
Okay.
again, because you really can't see them, I had a really, really difficult time. Like I told you, when I started in college and I was doing my electricity classes, I was acing them.
Right.
Because I could hold a relay. I could hold a
physically
contact.
see it.
I could see
Right.
switches opening and closing.
I can see things move.
But that was cool. But when it came to electronics, literally, if there was a grade lower than an F, I would have gotten it.
Because it just didn't click.
It did not click. So my father sat me down, and he was actually pretty upset that I didn't grasp this concept of electronics.
Mhm.
And he drew me a picture very similar to what you're looking at right now. And this is a plumbing tee. Now think about how a relay works. A relay has a coil and has a set of contacts. When we energize the coil, we create a magnetic field that causes a set of contacts to close.
Right.
So we have the coil that we energize or de-energize, and then we have the contacts that open and close. So my dad drew me this picture. And what this is, it's a plumbing tee. And since then, I've actually created these. When I travel around and I do classes, I actually created plumbing tees that actually have this pivot in it. So what you're looking at is a plumbing tee.
Mm-hmm.
The bull of the tee, the side, represents the coil of a relay.
All right.
Because that's what a transistor is. It's really a relay. I apply voltage to the coil and I provide a path to current to take. Yeah. So wow. So now the bull of the T represents the coil,
Right.
and the run of the T, the vertical path,
Mm-hmm.
represents the contacts.
The flow.
Yeah. So with
primary
that,
current.
with that red pivot the way it is, if I drop a ball in the top of that T, which Jocelyn is going to do right now, bloop, right? It can't pass through
Right.
because I'm not applying any potential to the coil. Right? So my contacts on my relay are now open, not allowing current to flow because I haven't applied any voltage to the coil. But now look what happens. Now, if I apply voltage, pressure now the path opens.
That's crazy.
And now my transistor is conducting.
That seems so simple.
You know what? It wasn't.
Right.
It wasn't when I was 18.
Right.
But so what happens, that's a really long pencil. But so what happens is when we apply a control voltage to the base of the transistor, now we open up this path for current to take. And once my father sat me down and showed me this, I literally aced all of my electronics classes from that point forward.
That's really cool.
It really clicked. And like I said, when I travel around the country and I'm doing classes, I always bring that plumbing fitting with me. And then the proverbial light bulbs start going on. People start getting it because electronics is really hard to see. Electricity is hard to see. You can't see it, touch it, taste it, feel it, smell it. Well, you can, but you'll probably end up in the emergency room afterwards.
Consequences of that.
Yeah, that's actually pretty cool. You put that in there. That's my favorite way to teach this stuff.
Yeah, I'm glad you put that together for us because I mean it makes sense to me. I mean, does it make sense to you, Jocelyn?
I'm a visual learner.
Yeah, there you go.
Yeah.
Awesome.
The same way, we're very visual, and so now I can see it and go, oh, that's very intriguing. Okay, is that making sense to everybody? I hope so, because it
just made sense to me.
Yeah.
I read the book last night, so I just figured it out.
I wouldn't be surprised.
There you go. Yeah,
I've been teaching this for decades. All right, so I get that, and so let's do a little reflection on this. So if we think about how we're flowing through our circuit, we talked about the N-type material, the P-type material. We can use that for, like you said, pretty much anything. Electronic component. Any technology that we're working, think about like that solar cell. I discussed it before. Now it's really making sense.
Think about a solar panel as a big diode.
Yeah.
That's really what's happening. A solar panel is constructed of a lot of solar cells, which are made up of diodes, which is a layer of N-type material and a layer of P-type material. And when you're dealing with a solar array is a bunch of solar panels put together. A solar panel is made up of a lot of solar cells.
It's
it's one of those on steroids. Yeah,
that's really all we're doing.
But when you think about any electronic circuit control, it really all boils down to that doped material and how layers of that doped material are put together. Now I'm simplifying it a little bit because when we create P material and we create N material, it's not the same. We're doping one more than the other. So there are a lot of intricacies in this because when we talk about even a transistor, there are NPN transistors, PNP transistors, there are MOSFETs, there are JFETs, there are BFETs. They're all transistors, but they all have different operational differences for different applications. So I don't know how deep you want to get into that.
I don't know. It's getting pretty deep for me.
But like NPN transistors, for example, they operate really, really fast. So those have really popular for high power applications. Yeah. Whereas PNP transistors, they function slower and they're good for analog circuits and different things. So based on MOSFETs, metal oxide semiconductor, they're all have different applications. They all function the same way.
Right.
So like a PNP transistor, the diagrams for these look exactly the same. One has an arrow that points in toward the center. One has an arrow that points out. NPN not pointing in, kind of neat. PN pointing in, so you can kind of figure out which one. Wow. Some operate with positive current flow into the gate or the base. Yeah. All right, which is what we call the coil on a relay, and some operate with with voltage coming out or current flowing out, but they really are exactly the same. The function is exactly the same. There is some transistor. So we have relays that are normally open,
Yeah.
and some have normally closed contacts.
Right.
So there are some transistors where the path is open.
Right.
Normally. And
when
then when you apply voltage,
pressure
it
voltage,
closes.
It closes it all.
Yeah. So like I said, so we have a bunch of like a JFET. Okay. So a JFET transistor is like what we call a relay with a normally closed set of contacts.
Wow.
So people go, people get, they want to get, NPNs and PNPs and
Right.
MOSFETs and JFETs and
Right.
they're all the same.
They're all switches and relays.
They're all the same thing. They're all layers of P material, 3 layers, 2
Okay.
P's and 1 N, or 2 N's and 1 P. But it's all the specifics. It's all the little intricacies that make them different for different applications. Some transistors function as amplifiers, where you put in a small signal and you get a big signal out.
Really?
So if you talk about, your amplifier on your stereo system, a stereo, wow, what's a stereo? But if you talk about an amplifier on a sound system,
right, we're amplifying the voltage.
it's just transistors. You're taking a small signal,
Yep,
and you're magnifying that signal at the output.
We can probably go ahead and get rid of the presentation if you want, Jocelyn, back to scene 1. So it's really making me think, we often talk about our inverters, and we talk about how an inverter operates. And if I'm thinking about how we control the speed with an inverter control, right? I'm normally thinking about a bipolar transistor, and all of a sudden I'm going, wait a minute, bipolar transistor. So my switches of an inverter are just the transistors.
Yeah.
Flowing.
So actually when we're thinking about an inverter, like an inverter controlled motor, an ECM motor, it's 6 transistors.
Exactly.
And there are 3 sets of 2 transistors.
Right.
And each set of 2 transistors is responsible for creating one phase of the artificial 3-phase signal.
Of a phase.
Yeah. It's the positive side,
right,
and the negative side. So think about, I don't have a graphic here, but think about 2 transistors where the emitter of one is connected to the collector of the other. And we send power into the gates or the bases of these transistors. And then as we energize and de-energize the bases of these transistors turn on and turn off, creating this artificial sine wave.
Yeah.
And then we create an identical artificial sine wave 120 electrical degrees after that one, 120 electrical degrees. Yeah. And by controlling the time lapse between the instructions, between the signal, the power signals at the then we can increase or decrease the frequency of the power supply being supplied to our ECM motor. Higher frequency, higher fan speed.
That's right.
Lower frequency, lower fan speed.
Wow.
But now, even taking a step back, ECM motors are 3-phase motors,
right?
But we power them with single-phase AC.
Yeah.
Well, we take that single-phase AC supply and we pass it through what's called the bridge rectifier, which is made up of diodes.
Right.
And it takes AC, converts it to DC.
Yeah.
Then we take that DC signal and we send it through these massive banks of capacitors to smooth the signal. Now we have a DC signal.
Yep.
And then that DC signal is sent through those 6 transistors, creating that artificial 3-phase. Yeah. So we're taking AC, converting it to DC, converting it to 3-phase AC, and then variable frequency drives.
Yeah.
Variable frequency drives are drives that have a drive where the frequency is variable. Mm-hmm. So in case you don't know, if you read Hebrew, you got HVAC licked. we right? People read English left to right. We read Hebrew right to left. So if you read HVAC right to left, you got this licked. Right? Variable frequency drives that drive where the frequency is variable.
Love it.
Kind of cool. It'll help you pass any test.
That's right. Let's remember that, Jocelyn, as we start diving into this. It's going to be the key to success. That's pretty simple.
At its most elementary level, yeah, it can get crazy.
Oh, I'm sure
I don't
it
want.
goes
I don't.
deep. Yeah, I mean, you can if you want to dive deep, you can dive into one of Eugene's books and get as deep as you want to go. So, any questions while we're here? There's so much great content. We're grateful that you're
But hold on,
hanging in
you got
with
me
us.
smiling, so we'll go.
Oh yeah, he's back to nice
We'll go
now.
nice now.
Yay, we did it, Jocelyn. Well, we're so thankful for you all. We hope that this helped at least allow electronics to be a little bit more comfortable discussing, so that when we're working with these circuit boards, and many of us go, "Ah, it's a circuit board. I don't want to work with this thing," but then you stop and you look at it differently and go, "Oh, you know what? We're really just controlling the flow of current like every other component that I've ever had in my hand. Now I just have to understand that I can visualize it. I'm not going to see it because it's so small, but this is what is actually happening. And I can help my students, or I can help myself realize that we're just controlling the flow."
But you know what's even funnier? If any of you have electric heated seats,
Yeah.
or cooled seats in
Heating
your
or
vehicle,
cooling, yeah. Where's the ductwork in those seats at?
yeah, there's no compressor, no
Right.
ductwork. It's thermoelectric. It's the thermoelectric technology that's heating your seats,
Right.
but also it's what's cooling your seats.
Because of the DC voltage,
Yeah,
we can
you
change
can
the
switch it.
direction of the
Yeah.
voltage.
So Clifton, you've seen the coolers. You can have a
Yeah.
cooler that'll keep food cool,
You bet.
or
hot.
cool.
Yep.
It's this.
Right. We're just changing the direction that we're applying the power to it.
Yeah, remember you have the cold side and
Yeah.
the hot side.
Right.
And if we switch those, we're going to change
the
Yeah.
flow of electrons, changing the flow of temperature.
It's kind of cool.
That is
And
wonderful.
or warm, depending on which way you plug it in.
Exactly.
Could be
All
heat,
right.
could be hot, could be cold.
Yeah, that's exactly right. Well, hopefully that answered everyone's questions. We had a lot of comments and questions after our previous episode, and it sparked a lot of curiosity. And that's really what we're here to do. We're here to help spark your curiosity, give you the resources to understand and to be more successful with these concepts, especially in the classroom. And if you have any more questions, concerns, let us know. We'll put links in the description to some of these parts, so you can pick them up on Amazon for almost nothing. Very easy to introduce into the classroom. And next week will be Christmas, and that following Thursday is New Year's. So we're going to have to decide if we're going to be doing classes on those. We'll get back on that one. We've got a bunch of things already scheduled for January. So if we don't see you, have a Merry Christmas, Happy Holidays, and Happy New Year, and we will see you all soon. Bye, everybody.
Take care.